be
fine. All right, perfect. All right, so today I'm going to talk about the conversational agent for e-commerce, just a very quick introduction about VUI. VUI is a startup founded in 2018, and we are located in Boston. We also have an office in Trento, in Italy, in collaboration with the University of Trento. Most of our team is focused on machine learning, also speech and conversational AI. Some background is from Amazon Alexa, Jibo interactions, and people from Nokia. So it's very, very focused on machine learning and natural language processing. So far, we have 35 people, and we mostly focus on e-commerce. So let me start with with a statement. What is the kind of problem we're trying to solve? So you're probably familiar with the e-commerce lifecycle, right? So there's a pre-sale stage where you're looking for a product, and you interact with a catalog, and so there are search queries, and there is a session that you go through, and then you probably find something that you're interested in, and you click, and and at some point you make a decision to buy something. So you go to the next stage, which is the sales process, where you fill the shopping cart, convert the shopping cart into a purchase, and then you receive potentially the product you bought through delivery, and then the product that you bought may have a problem, so you have questions. So there's a stage which is we call post sales, where it's more about customer care, and so you have, like I said, you want to return a product if it doesn't fit your needs, and or you want updates about the order which is not arrived, and things like that. So those are three stages that are very much different from each other in terms of data, in terms of user experience. So they are completely disconnected, and they even use completely different software tools. And like I said, the user experience across those three stages is completely different. So you interact with a search engine, then you interact with basically purchase steps that you need to fulfill your order, and then you probably deal with a customer care over the phone. So they are all completely different steps. But in here, an example, just next is a simple example of a real interaction between a customer and a sales representative, which someone trying to find a product and buy the product. Just 1 minute and something. Just want you to listen for a second. You will see on the screen. I also try to put a representation of what's the meaning of what the user said and the meaning of what the sales representative will say in terms of labels, so semantic representation. So it should be easy to understand.
My name is Erin, who I have the pleasure of speaking with.
Yes, this is Irene.
Irene, how may I assist you?
Well, I need to know, I was going to order a pair of boots, but it might not be in stock is what I'm thinking. So can you check the status on it?
Okay, I can go ahead and check a look. What is the size that you, the style number?
The style number is 17444, and the size is 6.5.
Okay, the 6.5 is still available.
Oh, it is. I'm amazed. Have you ever seen that boot? Is it a cute boot?
It's kind of have like a higher platform at the bottom, but it's pretty comfortable, flat level boot. It has like fur on the inside and around the tongue area of it.
Okay. Well, yeah, I want to order it, please.
Alrighty. So for your order, just provide me the customer number in the blue box on the back of the catalog.
All right, so as you can see, there's a lot of complex information exchange. Natural language is complex, but potentially you can reduce all those sentences, those utterances, to a simple meaning representation. And then you saw on the screen, the kind of a predicate argument representation, where for example, you can say ask info about the product, and those could be a way to somehow represent that conversation. The question is, can we actually automate that conversation completely? And that we need to deal with the very complex natural language, which can be ambiguous in many different forms. I mean, you can have lexical ambiguity, syntactic ambiguity, also whatever you put, a sentence in the context of a conversation, there's co-reference resolution. In the interpretation of the meaning, it changes completely because you need to know about the domain and other information in order to interpret things correctly. So if you want a funny example about syntactic ambiguity, if you have an Alexa Echo device, you can probably try the sentence buffalo, buffalo, buffalo that 7 times, which is syntactically correct, and you'll see a very interesting answer from Alexa, something we put into the device as a Easter egg, but just to sing as an example of syntactic ambiguity that you can actually face when you're talking to a device. If there's any questions, please let me know. Again, or we can keep the questions at the end. All right. So this is basically introduction to what we want to present, and then so I'll go through quickly the architecture of a conversational AI agent. I will talk a little bit about the natural language understanding. We'll focus mostly about the query understanding, and we'll give an example of query classification into more details. So let's see, conversational agent. So typically, conversational agents are task-driven dialog systems. So it does have the purpose, the goal to help a user to complete a specific task. It's not just open-ended like you may find in chat system, for example, but it's very designed to complete a specific goal. Typically, it's also built around an ontology, which is describing domain knowledge in a specific domain. It does follow the collaborative principles of Greece maxims, which means we're assuming that the user is collaborative, so they're not trying to cheat the system or to break the system, right? And there are typically a couple of approaches that you can find in terms of architecture. One is called the pipeline architecture, which is the classic one, or there is also more recently end-to-end architecture where we go from text to text or voice to voice and skipping all the intermediate steps, and we can see in a second what that means. Of course, the interaction with a dialog system could be text, voice, or even multimodal by combining the different modalities together. For conversational search, that's a specific variation of dialog systems because you're looking for interacting with a catalog. And so you need to understand when you're talking about a specific product and when you change the topic, and you can go deep down into the meaning of and into the questioning about a specific attribute or feature of a product. You can change completely in the middle of the conversation and talk about something else. So this is an example of conversation about refrigerators. So you're looking for refrigerators and you ask questions, and then you refer to products that you see on the screen. And I will see an example later on. So in terms of architecture, this is the classic pipeline architecture where you can see you start with, if you have a speech interaction, you start with a speech recognizer, which you translate things into text. And then you have what we call natural language understanding, where the meaning of the text is converted into semantic. And the semantic is actually fed to what we call the dialog manager. In the dialog manager, we put that specific interpretation in the context of a conversation and provide an action to execute. And that action is translated by the natural language generation into a full natural language sentence. And it depends also on the modality. It can include some graphical outputs, or if it is only voice, it will be probably a little bit more verbose in the tune for voice interaction. For e-commerce, there's a little bit of more complexity because all the conversation is often about products. So there is a tight integration with a catalog, and catalog can have 1,000 or millions of items, and it has a very very complex. But all that information needs to be converted into a model representation, a representation which is actually able to be transforming data for natural language understanding training. I will go to one example. Of course, in addition to that, catalog, there is all data that you need to, in order to train different models to understand what the user said. And I apologize, this is a very busy slide, but it's pretty much a pipeline system, so that many people here are familiar with. All right, just to give you an example of opening up a little bit of a box. So natural language query understanding is one of the components you need to have. It's probably one of the core components that you need in order to understand what the user said. And this is the module that will provide a meaning representation for the user input, and includes intents, entities, slot filling, normalization, disambiguation. We'll be able to, should be able to understand the product categories if it's a query, and should be able to understand a negation, for instance. Those are some of the features. And but this component, it's quite articulated in terms of models. And this is an example that the one that we built in our framework, which is a combination of different models. It's an ensemble from the text classification point of view, but also from the entities. We developed some of the algorithm to do entity consolidation, where you have multiple hypotheses about the specific entities, and you have the capability to fuse into a single hypothesis the prediction for an entity. So, for instance, you have a intent classification for, I'm looking for a cruelty-free moisturizer without shea butter. And that's typical, in the domain of cosmetic request. And that is translating to find intent, find a product, a task, a category, and so on. And in terms of techniques, there are many different techniques that you can apply in terms of machine learning. It depends on what's the distribution of the data. So for small data sets, we actually still use more traditional methods, but when you have a lot of data, of course, we push the envelope with the more recent deep learning approaches. But the best combination of those models is actually an ensemble of both. In our case. Let me just give you a better understanding of what is the output. So this is the same example, but we kind of dissected in all the different parts that are provided by natural language understanding. There is also, find intent is the typical label attached to this specific utterance. And you can see there is a product categories that are identified, like cruelty-free moisturizer, and also negation, right? So in this case, you want to remove the products that they are including shea butter into the ingredients. And this is also a model which is composed into the ensemble that you saw before. So at the end, this specific utterance, it's translated into a search query, which is actually fed to your search engine to build the proper query that exclude that ingredient, and you retrieve the ingredient in a window, like for example, at the bottom there is a chat system which is actually visualizing products that are somehow consistent with the request. All right, so how do we build a system like that? So here's an example. Just to give you an idea, so one of the classical approaches, to make the system robust, is to use bidirectional LSTM with conditional random field, where the input is translated, it's converted into embedding representations, but both for words or sentences and characters. You see so we had to add a component which is actually embedding at the character level to absorb what are, for instance, misspells and errors, to make the system robust. But you stack together those embeddings, and you can see here the character embedding is built on the CNNs, and then you stack that as an input to the conditional, the bidirectional STM, which is coding the context of the words, and at the end you have a conditional random field to optimize the probability to find the tags. All right, so this is just pretty, I won't say standard, but it's kind of common, but there are many other examples. What I want to focus next is to deep dive into one component so you can get a better sense of what's the mechanics, what a real system, industrial production system could be. And so we'll dig into what we call query classification. Any questions so far?
A short question. Is there the plan, or do you have a reason why you haven't not used, for example, BERT or other NLP models? Or is there a plan future?
Yeah, this is just one example, and we do have fine-tune BERT's encoders that actually used a sentence level, but the encoders that are used for to compress a little bit the representation. But yeah, I mean, it's just an example. That's a good point.
Thank you.
Yeah. So actually, to be honest, we are a little bit skeptical about using deep learning everywhere, like I mentioned, because sometimes just maximum entropy approaches are better for when the data is smaller and the distribution is always skewed. But yeah, so we do use those. All right, so query classification. So the query classification part is the very key to identify, given a query, what is the product that the query is about. And so it relies, it's a model that tries to extract the meaning or a topic of a specific query. That relies on what we call taxonomy nodes. They're representation of the product catalog taxonomy, so the way products are organized. And it does, you can see the example here. So what the query classifier will produce is the this is a level 3 taxonomy node called top freezer refrigerators, which is part of appliances, which is part of refrigerators, and so on. So this model is able to predict a multi-class, multi-label. So we'll go back to that in a second. And it has to be very robust because it's typically short and ambiguous text. It does leverage the hierarchy, which is built into the catalog, but it also a dual purpose because it does allow to improve the natural language understanding for brands and products. And also it's very useful for the dialog context interpretation when you have a conversational system. But just if you want to use this for search, it's the query classification is extremely useful to boost the product search relevancy and increase the recall, because it's very important when you don't have an exact syntactic match with the traditional search engine. This will give you the boost to retrieve other products that are relevant. And of course, I mean, it can also be used in auto-suggest, which is very common to produce a category while you're typing in a search. All right. And well, the other boxes are about business, but okay, let me go through this. All right, so let's go back to the how do we frame this problem? So we have a query and we want to those category taxonomy nodes. So those are a real example from real search in a very large catalog. So number stencil for painting, can be classified as a stencil. In the same way, garden hose connector can be classified as a garden hose quick connector with some probability. But reality is that queries are very ambiguous and they actually belong to many different categories. Also, the way the categories are organized is not always perfect. It's a very noisy organization. So what you really need is a model which is able to predict with very high accuracy the distribution or the probability of a query being belong to a specific node. So for example, the number stencil for painting, it does appear very often in stencils, but also in craft supplies, right? The same thing for other, and you see the pet wash glove is a little bit more long tail, so it's very unusual query, but it has a little bit broader distribution across multiple categories, right? So what are the challenges so far? So first of all, in this case, catalogs are very big, more than millions of products. the number of labels is also very big, so at least 3,000 or more. And the other issue that which is actually making this harder is that there's a very high volume of traffic, so the distribution of it drifting continuously. That means so manual annotation is not an option because it's very hard to understand what that query means. It's very expensive and it becomes very quickly stale. But also, it's very difficult to manually capture the fact that a query can belong to multiple categories. So we need to find something which is actually a better solution to somehow annotate the data. As a task, this is framed as an extreme multi-label multi-class text classification. And there's a lot of literature in this area which is actually trying to solve this very hard problem. But what, let me see. So what is the solution in terms of addressing the data? If you're familiar with eCommerce, so Clickstream is actually a source of, it's a data mine, it's a golden mine for data. So there's so much information there. If you have a way to filter the noise and extract the right information, so this could Clickstream data can provide you the annotation you need, and with the less ambiguity that introduced by a manual annotation. So what does it mean? You kind of capture the behavioral signal when the user is actually searching in a session. You say, okay, this guy clicked, after querying a specific product, they clicked on this product, on that product, and and you can also you can use many signals to decide if that clicks is actually a robust representation of that specific category. So in that case, so I'm not going to give the details about how to denoise this data in terms of behavioral signal, but there are techniques that will allow you to say, okay, with a relatively good accuracy that a query belongs to a category. So, okay. So the other challenge is how do you prepare the data? So data, it is a multi-class soft label annotation. It means that there are multiple labels that are valid at the same time. So when you do the split for dev, so training, dev, and test, you need to respect that distribution, which means it goes in 2 dimensions. One is the distribution at top level, but also horizontally, you have to make sure that the distribution is preserved in the multiple levels, so horizontally. So you want to make sure that, for the example that we gave before, for the stencil, you get 2 labels, right? In each one with a weight, which is a good representation of the distribution. And for that, there's we extended a little bit the algorithm presented by Konstantinos Sekidis for k-false 35 partitioning, and to make sure that whenever you split the data, dev and the dev set and the test set are a very good representation of the original training set. That's fundamental. All right. So for the example that I'm going to show you, we use more than 3,000 labels, 10 million samples for training, close to 1 million for dev and test. So I forgot one other problem is that because of the way those taxonomy are represented, there is no always a good amount of data representing the nodes. So, for example, very non-popular nodes in the catalog may get a little attention in terms of clicks. So what you need to do is to do some pruning and merge, some of the products that got clicks, very few clicks, into the above category, so that it's a little bit more general, but still valid in terms of representation. This will allow to reduce the distribution skew, the data skew distribution for the training process. And there's a paper where this is describing very detailed. All right. So finally, so there's another little issue here that you need to address. And like I said, it's a multi-label problem. So you need to do a couple of things to reduce the number of labels that are predicted. So imagine if you use a softmax, for instance, as a layer in your network, you get a 3,000 labels, each one with a specific probability, which is not exactly what we want. So we need to apply what we call, sparse max activation function, which is the one represented there, that allows you to truncate the labels that are all relevant. So you get a sparse representation with 3, 4, maybe 5 labels maximum. But that's just replacing that layers with sparse max is not sufficient. You also need to use a sparse max function, loss function, that will train the label in a way that actually is sparse. And that function that you see, loss function represented here, which seems not very differentiable, is actually the one that will do the trick and make sure that the prediction are actually produced in a sparse manner, so that you have a better representation in terms of training when you actually train your model. And the interesting part, there's this paper that shows in details that this sparse function is actually differentiable, so you can do backpropagation without any problem. It's actually very elegant. Yes, there's a question, Roberto.
Yeah, sorry, probably I missed something, but I'm not sure I understand where this data come from. Data used for training, testing, and so on. Yeah.
So the training, so the data. Okay. Let me see. Clickstream. So probably I didn't explain well the Clickstream data. So imagine a lot of people interacting and searching through a website, right? And you get all the logs from the search. So people will show, okay, I'm looking for pet glove, pet wash glove. In some people click on a specific product. Some other people click on another category. So you collect all this information. You apply. So imagine there are 100 people that click on a specific category, which is clippers, scissors, brushes. And that is likely going to be a very valid label to categorize that query. So you capture what we call behavioral signals to detect what the user preferred among a list of possible results. So that.
But sorry, Pino. You start from an existing search engine.
Yes. So there is there is a massive amount of data which is produced every day from a search engine. And so I missed that part.
Okay.
Good point. And so that, imagine all the logs from the search that accumulated. Like there are, in this case there are millions. And then from that data, you throw part of it by a process which is called denoising. So things that are not realistically correct, you throw in the garbage. But the one that are very confident, you use that as a label. So pet wash glove will likely be clippers, scissors, brushes labeled because 100 people selected that in the last 3 months, something like that. And that's actually super. Yeah, sorry, go ahead. Sorry.
No, say.
What do you say?
Yeah, got it. Yeah.
All right, cool. This is actually extremely robust because it doesn't need you to know the domain. Because if I had to understand, the domain for home improvement, I will go crazy because I have no knowledge to do that. But because the user is actually the intent of the user is very precise, then you get very good representation. All right. So sorry, I'm taking a little too long. Apologize to Francesco. A couple more minutes. Okay. So then, so we trained that model, and so just to give a sense, so to train that model takes like 4 days on a medium large GPU, but so we get those results that are significantly better than a single multi-class model. So because we kind of representing better in a better way the problem, and so you get precision recall. And DCG is a way, a metric that it's normalized the DCG. It's a metric which is very much used in search, but precision recall is probably more familiar with that. It's a 10 point, almost 10 points difference between the traditional approach. But I want to show you just quickly the results, because this model is able to produce a good representation of what a query is. So Leona Silver, it's a tile, and you get a very high probability on the tile category, but also you get a little bit of probability on the tile samples. And you can see, for example, also the robustness for spelling correction. Broom, which is misspelled, it's highly classified with the 74 for brooms. Ice scrapers is also correct because there are brooms for ice scraping, and so on. The other features of this model is that if you get a uniform distribution for a query, it means it has no meaning. So this number, it's probably an ID, product ID, and has no meaning in terms of category. It's just a flat probability. And last one, also you get a chance to see that, for instance, some of the lightning force sealing is actually it's not a node ending, but it's not a leaf in the taxonomy. It's a node because it's more referring to a generic sealing lights categories. And you get a very good distribution across many labels with a shared upper node, so which is extremely useful information, which has been learned by the model. All right, so just wanted to wrap it up. Sorry for taking this long. Let's see how we did. Imagine now that we have a full system which is using all the components that we trained, and this is just one piece of it, and this could be the result.
Welcome to VUI. How can I help you today?
I would like to know when my order will be delivered.
Your most recent order has shipped with an expected arrival on Monday, March 3rd. Is there anything else I can help you with today?
If it doesn't fit, how can I exchange the order?
Of course, for a rapid exchange, you can call our customer service specialists at 888-678-5576 to place your new order and process the exchange. Is there anything further I can help you with?
Can I exchange in-store?
Yes, here's our closest store location. Can I help you with anything else?
Can you show me a red petite size dress that can be machine washed?
Here's what we have available.
Does it come in charcoal?
No, but it does come in river blue. Here's a similar style dress in washed gray.
I am also looking for a pair of red shoes in size 9.
Here's some shoes that are available in red.
Do you have it in black?
Unfortunately, they only come in navy and red.
You're very smart.
Thank you. The more we talk, the better I can assist you.
All right, so, sorry. All right, so that concludes my talk. I want to also thank you, Evgeny, Amir, and Surya that collaborated this work. If there's any question, I apologize for taking too much long. Francesco, I went over a little bit. But yeah, I don't know if there's time for questions.